Hello! We talked about strict dominance last time. A strategy strictly dominates another strategy if the utility is always strictly greater regardless of how the remaining players play. A similar notion is weak dominance, where the utility is not always strictly greater and there can be equality in some cases. We start with the definitions. For two strategies SI1, SI2 for player I, we say that SI1 weakly dominates SI2 if, for all the strategies that the other players play S minus I, UI of SI1 S minus I is at least UI of SI2 S minus I. And this inequality is strict for at least one possible strategy profile S minus I. This means that playing SI1 is always at least as good as playing SI2, and playing SI1 is strictly better for at least one instance. If some strategy weakly dominates SI, then SI is weakly dominated. On the other hand, if SI weakly dominates all strategies for player I except for itself, then SI is a weakly dominating strategy. Take a look at this example here with a payoff table for a two-player game. Can you find some weakly dominated strategies? We see that Z is weakly dominated by X. When player 1 plays A, the utility for X is strictly greater than playing Z. And when player 1 plays B, the utilities are equal, so the utility for playing X is at least the utility of playing Z. Now notice that Z is not weakly dominated by Y, since they give you the same utilities. There is no case where we get strict inequality. Now we have a procedure similar to IESDS called iterated elimination of weakly dominated strategies, IEWDS. Here, we are removing weakly dominated strategies until there is only one strategy profile. Looking at the same example above, we see that Z and Y are both weakly dominated by X. Eliminating these two strategies give us this smaller game. And we can easily see that A weakly dominates B, so we can eliminate B to get only one remaining strategy profile, AX. And once again, we will claim that AX is a Nash equilibrium. We have this theorem here. Suppose G is a strategic game. If IEWDS ends with only one strategy profile S star, then S star is a Nash equilibrium of G. We will leave the proof of this as an exercise. Note the main difference between this theorem and the one for IESDS. In a strict case, the theorem claims that the Nash equilibrium is unique. But in the weak dominance case, here we can no longer claim that the Nash equilibrium is unique. A different sequence of eliminations can result in a different Nash equilibrium. As an exercise, take a look at this payoff table and see if you can show that two different applications of IEWDS here could end with two different profiles. So what is a key difference between the strictly dominated case and the weakly dominated case where we might not get a unique Nash equilibrium in the second case? Well, unlike strictly dominated strategies, which cannot appear in any Nash equilibrium, weakly dominated strategies can actually appear in a Nash equilibrium. So when we eliminate some weakly dominated strategies, we might eliminate some of the possibilities for a Nash equilibrium. In fact, some Nash equilibria cannot be found through IEWDS. For example, Bach or Stravinsky has no weakly dominated strategies. So this procedure might not always work, but when it does, it will give us a Nash equilibrium. Now let's move on from weakly dominated strategies to weakly dominating strategies. Now recall that strictly dominating strategies are good ways to play a game. They will always appear in a Nash equilibrium. And just like strictly dominating strategies, weakly dominating strategies are also good to play, but in a slightly different way. We have the following result. If for all players I, SI star is a weakly dominating strategy, then S star is a Nash equilibrium. As usual, we will leave the proof as an exercise. So this means that if everybody plays their weakly dominating strategy, then we get a Nash equilibrium. In the next lecture, we will discuss a game that has a weakly dominating strategy, which is a special type of auction.